All right, so today we're going to talk about convolutional coding. We talked about linear block coding last week. Lots more to cover in these topics, but hopefully able to give you a good introduction to this material, looking at some of the classic things involved in block coding and convolutional coding. So we'll talk about convolutional codes, the generation of them. We tend to analyze these using state diagrams and in particular trellises. We've looked at these before, but now this is a new application of the same type of visualization tools. We'll look briefly at hard and soft decisions and go through a decoding example using the Viterbi decoder for hard decisions. I'll explain what all that means here as we go through this. Not sure if we're going to finish today. We'll wrap up on next Tuesday as needed, and then also cover some kind of source encoding. Right now we're doing channel encoding, right? So yeah, another class of error-controlled coding that is distinct from block codes. And so there's a number of others, but other types of code, but they largely fall between block and convolutional codes, and some of the more recent and exotic type of codes may draw from both of them. Yes? Did someone say something?
Sorry, no, it must have been a distortion. You're good.
Okay. All right. So now one of the things that's different about convolutional codes is that we typically only send a parity bits. It's not fundamental to the idea of convolutional codes, but typically we're not actually sending the true message bits. Now, if you remember, we use this term systematic codes. And in block codes, we are often using systematic codes, and so we're sending the original message bits along with the parity check bits. In this case, we typically only send the parity bits. The information in the message bits is spread out through several parity bits through this convolutional process. It's very well suited for burst errors, while block codes really excel at errors due to random noise. And what's the difference there? Well, a burst error might be some interference, or you move through a deep fade where the radio propagation, the signal strength drops suddenly and stays down until you continue to move out of that faded area. That fading could be due to a cancellation effect, a destructive interference between two different paths, signal paths to the destination, or it could be blocked by a building or a wall or something like that. Could also be some momentary interference at high frequencies, HF, which kind of ironically are now considered very low frequencies because we do so much of our work in the microwave region. But HF is more like around 3, 7, 10 megahertz type of thing. And their lightning interference is a big deal, right? So these type of interferences can affect multiple bits in a row. When we talked about our binary symmetric channel model before in the block codes, we assumed that the error probability of each bit being sent was independent of any of the others. It's not the case in a burst. That if you have a burst interference, then the probability of a subsequent bit being in there is affected by the previous probability. Was someone saying something?
Sneeze, Professor.
Oh, okay.
Don't
Sorry.
worry. You're good. Please continue.
All right. That's in contrast to random Gaussian noise type of thing, where these interferences are just due to random noise, and it's not dependent upon previous ones. In other words, it kind of has a Markov dependency. So these codes have memory. That's really the thing that distinguishes them from block codes. The impact of a single bit is spread over several output parity bits. Another way of looking at it is a given parity bit includes the effects of the current and several past input bits. The memory depth that produces this effect is denoted as a constraint length. Again, notation varies between authors, but K is a common variable used to denote this, right? It's K or L or N, usually a capital letter. So this results in 2 to the K minus 1 different states that this system can take on. So anytime you have memory in a system, whether it's a communication system or anything, if you have memory in it, then it has a state associated with it. So all right, so what does this look like mathematically? So we're going to have a generator, a polynomial that will denote with lowercase g, and our message bits are going to be x, and we're going to sum over some length, this constraint length k, and of course we'll do a modulo 2 operation on the results, so we end up with zeros and ones instead of zeros, ones, and twos and threes, and that type of thing, right? So each of these PIs are a different set of parity bits, and n is your time variable here, and so this looks like a convolution, right? So you've got a variable or a signal, let's say, that is being slid across another function, and it's multiplied and added up. So that's where the name comes from, the convolutional code. So each PI or GI is associated with a different generator polynomial that produces a different set of parity bits. So remember, in a block code, we could have a number of different parity equations that take that same input message bit and message word and generate different types of parities by combining the bits in different ways. And so here we have the same type of thing, whereas it's distinguished by different generator polynomials. So we normally interleave these at the output. So I explain that here on the next slide. So we also have a concept of code rate here. It is possible to have multiple input bits for each convolution, or a small case k greater than 1. But it's common to process each bit continuously, so we'll we'll call k equals 1 in this case. It's not exclusive, but for the examples we'll look at in this course, we're going to assume k is equal to 1. You can, like I say, look at multiple input bits at a time. You recall in our block codes we had k's that were some length, and then we added some parity bits to that to expand that code word to n, lowercase n, right? So here our k is going to be typically 1, and the code rate is going to be this number of generators, right? So here we have this g sub I. If I ranges from up to 2, then we'll have a code rate of 1/2. If we have 3 different generators, we'll have a code rate of 1/3 and stuff. So, and as you might expect, typically the more generators we have, the lower the code rate, the more powerful the code. But of course, it takes more time to send that. So, for example, on the 1/2, we'll see how these parity bits are interleaved to produce your output data stream. So you have some message bits coming in, and we're going to output the parity bits, p sub 0 from generator 0, and n is equal to 0. Then we have the other generator produces a p sub 1 at time n equals 0, and then we go to the next input bit. Now n is equal to 1, and we calculate an output p0 and then p1, and so these are interleaved as time goes on. So we can look at this mathematically for our generating equations. So g sub 0 will, this is a very common code for k equals 3, where we'll have a parity check that's composed of the current input sample, the immediately previous one, and the one before that, and then no effects, multiplying by 0. So our constraint length k is equal to 3 here, and we'll just call this for shorthand a 111 generator. Likewise here for, sorry, where did I go? I'm lost now. Okay, so here we have a second generator polynomial, and this is going to create its parity bit by summing modulo 2 addition of the present bit and the second oldest, or the bit two time steps in the past. All right, and we'll call that a 101. It's a little bit easier to see here if we expand this now. So we have for P0, this G0 produces xn plus xn minus 1 plus xn minus 2. And P1 is now going to be xn, the present value, plus xn minus 2. And this is all, of course, modulo 2 addition. Now, we can look at this as an, we can characterize this using an impulse response, right? That's how we would look at a linear system. We would put in an impulse, we'd look at the impulse response of it, and that tells us a lot about the system. So an impulse is a delta function, so our input might be 0, 0, 1, 0, 0, right? And so that's approximately an impulse function. So this table over here shows kind of our states, or the values that we would add up for this xn minus 1, and xn minus 2. Really, the memory of the system are represented in the xn minus 1 and xn minus 2. So the right-hand two digits here would represent the memory in the system, whereas the left-hand digit would represent the present or current value. So if we start with this 0, 0, we'll work from right to left here as this is working its way into the system. And so we'll, if we initialize the system at 0, 0, with the memory in the system, then as we put in a 0, 0, then of course with these equations the outputs will be zeros, right? So then the next step is the same. We still have just zeros, but then on the third step, now we'll have a 1, 0, 0 into the system. And so if we look up here, then P0 is going to equal 1 plus 0 plus 0, and P1 is equal to 1 plus 0. So we'll have ones in those locations, and for both P0 and P1. And then in the next step, that one will move into the first memory location, but our present current value it returns to 0. It's an impulse function, right? So now we'll have, in this case, P0 is going to be a 0 plus a 1 plus a 0. So that's a 1. And P1, though, is 0. We skip over n minus 1, and n minus 2 is 0. So that code parity bit is a 0, and so on. So now when we do the next time step, that 1 moves over to the second memory position, x minus n minus 2, and so P0 is still going to be 1. Okay, we're going to have 1 here, and P1 now is going to be 0 plus 1, so it's going to be a 1. Note that here we're spreading the effects of this 1, this impulse function, over multiple parity bits. Okay, so now as we output it, we'll interleave these things. So we'll have I guess it depends on which direction you're going, but you'll have 0 plus 0, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0. So that's that interleaving process. Now, a little easier to see, perhaps, if you look at the shift register implementation. It's a very common way and straightforward way of generating this. Here, xn minus 1 and xn minus 2 represent your historical or memory aspects of it. So data flows in on the left and moves to the right. And again, since it is not a systematic code, the data just falls off into oblivion over here on the right-hand side as we clock it through. So this is the modulo 2 operation, where we have this 1, 1, 1 type operation, right? So these are weighted by just a 1 value. Okay, so that's generator G0. This would be generator G1. And here we have a 1, 0, 1 type of operation. This is the interleaver. So on one clock sample, we'll read from the P0 here, and then we'll switch and output the P1. This rate is going to be twice the rate as the data coming in. All right, and these are modulo 2 operations again. So okay, so now let's just step back and think about some of the trade-offs here. if we have constant power, okay, then, and thinking about this in the context of Shannon's capacity theorem, right? So our code rate of 1/2 means that we're outputting twice as many parity bits per time sample, unit of time, than we have message bits, right? So we need twice the bandwidth to do that. The energy per output bit is 1/2 of that relative to the input. So you might think, well, wait a second, that's going to cause a problem, right? We need twice the bandwidth, and but the energy in this input bit is spread out over multiple bits. And so isn't that going to cause our capacity to decrease? And yes, it does, but we have gain that is provided by the structure of this data that helps us be able to detect and correct errors. So if we have a suitable structure in the data, then we overcome the impact of this sending these redundant bits, right? And alternatively, if we constrain the bandwidth, then maybe we use Comm or QPSK to take these two output parity bits per input bit, right? So now we can encode that to a particular constellation point, Comm, or both Comm and QPSK. When we don't have a number in front of it, it means 4, all right? So the quadrature Q implies there's 4 constellation points. And so we can encode 2 bits into each of those, into one of those constellation points, right? So, but when we do that, we know that our distance is decreased, the distance between these constellation points. And if we reflect back on our prior lessons, we realize that our performance will degrade somewhat, our bit error performance or packet error performance, or symbol error performance. So, but again, we're relying on the structure for improvement. So I say this because coding doesn't come for free. There is a trade-off associated with it, but it does produce improvements. So all right, so now let's look at distance just kind of briefly. So the system still provides a set of code words, as in block codes. They're generated differently, but we still end up with this kind of set or family of code words. We can look at that smallest weight non-zero code word, right? The weight, recall, is the number of bits that are 1 inside a fixed length code word, and that's the weight of it. And when we compare that to the all zeros code word, that gives us the distance between them, right? So the weight of the smallest non-zero code word kind of sets that distance. We call this the free distance in convolutional codes, but it's analogous to the Hamming distance. It's providing that same type of coding protection, an ability to detect and in some cases correct for errors. All right, so now we can look at this in terms of a state diagram. And here these states are represented or reflect these memory locations, right? So that's the state of the system as we get a new input. Okay, so we have state 0, 0, so we just have zeros in that xn minus 1 and xn minus 2 position, 0, 1, 1, 1, and a 1, 0. Okay, and so this state diagram describes the transitions between these different states. And so we might just loop here, or we might transition from one state to another. Now, if we recall what we know about state diagrams, this first digit associated with these transition arcs is the input into the state machine. The two digits after the slash are the outputs, right? So the output bits. This is a code rate 1/2 code. So we'll have 2 bits output for each bit input. We could have a code rate 3. We just add a different unique parity check, parity equation, and we have another modulo 2 adder outside it, right? So we can use the same shift register structure, but just add another modulo 2 adder, and then we just need a different combination of these bits, maybe xn and xn minus 1, or conversely xn minus 1 and xn minus 2. Probably an xn and xn minus 1. So we're capturing that input bit each time. So all right, so that's state diagram, but the trellis diagram is very useful in this situation. Recall that it also captures the state transitions of a system, but it's expanded over time. So we can see how the system evolves over time, or potentially evolves over time. And so again, here, these values on the left represent each unique state of the system, right? So for k is equal to 3, we have 2 to the k minus 1 states. So that's 2 squared, or 4 different states. These are the memory bits that we have in the system, right? So we'll have 4 different states. So we'll have 4 different kind of horizontal lines or sets of state nodes here, and then they're lined up in these time steps shown down here, right? So each vertical line, if you drew a line vertically through each of these states, that would reflect a different timestamp. And time increases as we move to the right. We have an input bit denoted on each of the state transitions, and we have the output parity bits also that's associated with this. So you see that these outputs are a function of what state we're presently in and the input, right? So if you were writing this in a function notation, it would be a function of the current state and the input bit, right? So so we tend to start with 0, and then we tend to flush the system with zeros at the end of a block of message bits that we're sending, so that hopefully we end up here in the top right hand corner with enough zeros. We should get there. So not absolutely necessary, but often happens. So so we can see here, if we start at 0, 0 and we get a 0, then we stay in that state. If we get a 1, then we move to state 0, 1. Okay, but we output a 1 and a 1 in that case. Okay, so now decoding. We want to estimate the original message sequence based upon the received bits and the knowledge of the coded structure, right? So our receiver only sees these input parity bits, and it's trying to make the best estimate of them, but we know that there's going to be errors in that system, right? At some random rate, randomly at some rate. But we know the structure of this, what it should look like. So we try to match that up, and we try to match it up over time, right? So we are not just looking at a snapshot in time now, but we're trying to look at, okay, I know that this system should evolve in a certain way given certain input bits. And like, for example, there's should be no way to go from this initial state down to the 1-1 state, right? That's an illegal state transition. Likewise, if you're here at the state 1-0, then there should be no way to stay in that state. That's a impossibility. All right, so we can use hard decisions. Now we use the bit decisions from the threshold detector in the receiver, or we can use soft decisions. What do we mean by that? That means we basically skip the threshold stage and use the integrated voltages from the output of the sampler at time t. So here's a correlation receiver, one implementation of that, and basically we would just throw out this threshold, and we would look at these voltages here, right? And the same thing here in a match filter receiver. We're just going to look at that one. Now, we are still probably going to select the largest of these, but that's not necessarily going to map to a 0 and a 1. When we do a hard decision, we're thresholding that voltage to the idealized logic levels, right? And so ultimately that's going to end in a 0 or a 1 for our logical bits. But the soft decisions will leave in terms of the voltages. So this way, let's say we have on-off signaling, and our idealized values is 0 and 1 volt. Okay, and so our threshold would be a half a volt, right? Anything greater than a half a volt is going to get mapped to 1, and anything less than a half a volt is going to get mapped to 0. Well, there's really a big difference between 0.99999 volts and 0.50001 volts, right? There's a lot of difference between those, but they're going to both map to a logical value of 1 if we use hard decisions. But if we use soft decisions, we retain that information and understand that, you know, if we have a 0.50001 type voltage, that its likelihood that that's actually a 0 bit is a lot higher than if we had received a voltage of 0.99999, right? So even though they would both get mapped to a value of 1 based upon our threshold device, right? So we're trying to capture that information and make better use of it, right? So hard decisions are basically throwing that information away. So soft decisions, whether it's in a whatever kind of decoder we end up with, that's generally going to produce superior results. Okay. All right, so let's look at kind of the classic algorithm. This is the Viterbi algorithm, another fellow that's kind of quite famous in this world here. Where do I have that? Got him right here. That's a picture of him right there. So he is a professor at USC. and the School of Engineering is named after him. That's how famous he is. He's in his 80s now, or maybe even 90s. No, I think 80s, so high 80s. He developed this, and basically, he published it. That entered the public domain, and is ubiquitous. So the urban legend is that he didn't make a dime off of this, but don't cry for him, because he was one of the founders of Qualcomm, and so he's done quite well. Qualcomm, of course, is a very dominant manufacturer in mobile communication systems, and holds a lot of patents. So they make a lot of money, not only off of their chips and chipsets and that type of thing, but also over their patents. So all right, fun facts to know. So very significant figure in communication systems. So the Viterbi algorithm is a maximum likelihood detector. So we're in its base implementation, we're assuming that we have equal probable bits coming in, or events. So then we can use a maximum likelihood detector. And yeah, there's some assumptions here that the error probability is less than 1/2, and that type of thing, which is normally satisfied for practical systems. So all right, so what we're going to do is we're going to calculate a branch metric for each time step of the data. So this is basically a difference in the received values versus the expected values. Now we're going to add that to the path metric, which are summed values for each possible path through the trellis, right? So let's go back and look at our trellis here. So there's all sorts of different paths we could take through this trellis, okay? And we're going to have a certain set of bits that are received. And for each of these branches, at a given time step, for each of these branches, there's a pair of, for this code rate 1/2 code, there's a pair of bits, parity bits, that we're expecting, right? We received some particular bits, and we're going to compare those for each of these, and we're going to create this branch metric for each one of these potential paths into this new state here. Then we're